We're going to talk about phase changes, and I thought we would start by talking about what the phases are. If we list the phases from low energy to high energy, the lowest is the solid phase. That's where the molecules or atoms or particles aren't moving very much. Liquid is kind of the mid-ground, and gas phase has the highest energy. We say that because in the gas phase, the gas molecules are moving very quickly. They have high kinetic energy. Now, anytime we're moving between phases, each one of them has a name. So we've talked a lot, like I said, about this one. Going from the liquid phase to the gas phase, that's called vaporization. But there are names for each one of these. So going from solid to liquid, that would be what we call melting. Sometimes that's also called fusion. That might seem a little bit weird. And if we totally skip the liquid phase, if we go from the solid all the way to the gas phase, that one is called sublimation. Okay. So those are all going up in energy. Those are all endothermic, meaning that we have to put energy into it to make each one of those processes happen. But now if we go down, so if we talk about things that are exothermic, where they release energy when they happen, going from a solid to a liquid is called condensation. Going from a liquid to a solid is called freezing. And if we totally skip the liquid phase and we go straight from a gas to a solid, that one is called deposition. I'm just going to change where I wrote that just so that it isn't real confusing. Now again, anytime we're going up in energy, those are endothermic. And anytime we're going down in energy, which is all this side, those are the exothermic ones. Now in this video, we're going to talk about all the phases. I am going to touch a little bit more on sublimation and the freezing and melting. And we're also going to look at some phase diagrams, which are going to help us see how intermolecular forces kind of dictate the characteristics of condensation and vaporization for each molecule. Intermolecular forces really decides what set of conditions that a substance will condense under or sublimate under or melt under. And so our phase diagrams are going to show us kind of how all those phases come together under different set of conditions. So let's talk a little bit about sublimation. Sublimation is going straight from a solid to the gas phase, skipping the liquid phase. Now, every molecule out there will sublimate under some conditions, but usually it's not conditions that humans would be present for. They're definitely like laboratory-made conditions. We only have a very few molecules that sublimate under room pressure that humans could be alive in. And those molecules that you might be aware of are things like carbon dioxide. Solid carbon dioxide is what we call dry ice. And dry ice, if you've ever seen it, it looks like a block of ice, but it never gets wet. It never turns into a liquid. It just kind of makes this gas around it, and that's called the vapor phase or the gas phase. And so dry ice is called dry ice because it never makes a liquid, unlike our water ice. Something else that you might have seen or kind of be aware of is iodine, I2, solid, will sublimate not exactly at room temperature. It will do it at room pressure, like our kind of normal atmospheric 1 atmosphere room pressure, but you need to heat it up just a little bit. So you need to get it a little bit hotter and then it will sublimate. So when things sublimate, molecules can kind of go directly from the solid to the gas phase, and we call that the delta H of sublimation. So it might also be written like this, delta H of sublimation. And It takes energy to make this process happen, so we call it an endothermic process. And another way to say the delta H of sublimation is the enthalpy of sublimation. That's the same thing as the delta H of sublimation. Now, the more energy it takes to make something sublimate, the more attracted the molecules are to each other. So this can be, just like delta H of vaporization, this can be a way to measure or to observe intermolecular forces. Now, when molecules sublimate, what happens is first the surface molecules that have enough energy, they sublimate, and so they kind of break free from the surface, they become a gas, and they go through the sublimation process. When we're going in the opposite direction, when we have vapor molecules, gas phase molecules, that turn into a solid, we call that deposition. And I kind of think about the word deposition as like deposit. The gas molecules are depositing themselves on a surface to become a solid, so we call that deposition. Now, when molecules sublimate and they turn into a gas, that gas has a vapor pressure. So just like we talked about how liquids have to have enough vapor pressure to meet atmospheric pressure, and that's what we call boiling, when the solid has enough vapor pressure to meet atmospheric pressure, it will sublimate. So here's a couple pictures of I2 sublimating, and I just kind of wanted to point out some things that are going on in this picture so that we can kind of describe what's going on. So I'm going to look at this picture first, and in this picture there's a hot plate. So that hot plate is giving energy to that Erlenmeyer flask, and then there's a little gray solid in the bottom here. That's I2 solid. Then in the Erlenmeyer flask, you can see there's this test tube, and the test tube has ice in it. And so that is cold, so that this entire thing is very cold. So we're creating a situation where it is hot at the bottom and cold at the top. Now what happens when you start to heat that I2 is that it starts to sublimate. So this solid that's in here actually starts to become a gas, and it starts to fill the Erlenmeyer container. Like this. Okay, so once the gas starts to reach up to that cold place, it interacts with that cold test tube. We actually call test tubes like that are filled with ice, we call them cold fingers. That's something that you might come in contact with if you go on to organic chemistry. So now this I2 is interacting with the cold finger, okay? And I want to transfer over to this picture here. So we can actually see, if you look at all this stuff in here, it's all purple. That is I2 gas. So that purpley stuff is gaseous I2 that has sublimated. And you can see that once it reaches the cold finger, it starts to deposit itself on that surface. So it starts to make a solid once it hits the cold finger and the energy is taken away. As soon as it hits the surface, that cold finger sucks back the energy to melt the ice, and it takes the energy away from the gas molecules, and they turn back into a solid. So they stop moving around as much, they can pack together a lot more tightly, and that's what we call a solid. So we have I2 gas down here, and we have I2 solid on the cold finger. And so that is the sublimation process, and then the deposition process onto the cold finger. Now again, like we said, not many molecules have the right kind of intermolecular forces so that they do this sublimation or deposition process at about 1 atmosphere. Sometimes for sublimation, we usually have to put things at very low pressures, basically pulling them apart to make them to a gas. So there's not many molecules that do this, but iodine is one of the ones that we kind of have in our everyday life. Iodine is what they used to use to kind of clean up wounds. We don't use it as much anymore. We don't use it as a solid. We actually dissolve the solid into water to make a solution, and that's kind of that orangey solution. If anybody's ever dabbed that on your arm or like on a cut or anything like that, that's I2 that's been mixed in with water. So we have I2 in kind of our everyday lives. The reason why when we do this experiment in the lab, we have to do it in the fume hood, because if any of the gas escapes through here, I2 is really caustic to the lungs. So if you breathe it in, it really causes a lot of damage to your lungs. So this is an experiment that we can do. We just have to do it back in the fume hoods in the back of our lab. Okay, and I also just wanted to touch on melting a little bit. I don't think that melting is necessarily super exciting. Melting is just going from a solid to a liquid, just something we see a lot of molecules do. The reason why I want to touch on it is because in chemistry, sometimes we call melting fusion. And that's just a kind of a weird word that gets used, and I don't want it to confuse you later when we see it in our diagrams. So melting and fusion for us are going to mean the same thing right now. And we talk about melting like ice. So if you put an ice cube on a countertop, it's going to melt into a liquid. We don't always talk about how, and I'm going to go to the bottom really quick here, that melting and freezing are the opposite of each other. So something's melting point and its freezing point are actually the same temperature. Okay, that's going to come up later when we do our colligative properties lab. But when we think about the temperature in which something melts and the temperature in which something freezes, so the melting point of ice is 0 degrees and the freezing point of liquid water is 0 degrees. So we're just looking at it from two sides of the same process, but the temperature there is always the same. So now I want to put all these phases together in something called a phase diagram. A phase diagram describes what different physical states and phase changes occur at different temperatures and pressures. So each region represents a different physical state, and there are lines on these diagrams that represent state changes. So when I say state changes, I mean phase changes. Those are the same thing. Okay, and I'm going to kind of go through a phase diagram and show you which each one of the parts means. Okay, so let's talk about kind of the major things that are going on here first before I start adding some more. First of all, this is a graph of pressure. So pressure is increasing on the y-axis here, and temperature is increasing on the x-axis. So when you think about those, up here is high pressure, but low temperature. Okay, so high pressure means the molecules are being squeezed together. Low temperature means they are not moving much. And that means, so when molecules are being squeezed together and they're not moving much, that means that they are going to be in the solid phase. So this solid phase tends to be high pressure and low temperature. All right, on the opposite end, at low pressure and at high temperatures, we have mostly gas phase things. So low pressure means that the molecules have lots of room. They're not being squeezed. And high temperature means they're moving quick. Those things describe a gas. So under those conditions, low pressure and high temperature, we have mostly the gas phase. And at kind of average pressures and mid temperatures, we have the liquid phase, kind of the phase in between solids and gases. All right, so I want to start kind of talking about the curves that are, not just the regions, but the curves that are on this phase diagram. And I want to go through one at a time, right? So I'm going to talk about this line. I know it isn't exactly a curve. It looks more of a straight line, but sometimes it's more of a curve. That is moving between a solid and a liquid. So anytime we go from solid to the liquid phase, we call that melting or fusion. And if we're going from the liquid to the solid phase, we call that freezing. So we call that sometimes the fusion curve. This line between those two phases is sometimes called the fusion curve. Right. Now let's talk about this one. Okay, so this looks a little bit more like a curve. That's going from the liquid to the gas state. Going from liquid to gas state is called vaporization. And if we're going from the gas state to the liquid phase, that's called condensation. So this curve here is sometimes called like the vapor pressure curve, because it represents different pressures in which something is going from a liquid to a gas, different pressures at which something is vaporizing. Okay, and then the last one we have is this one down here. That is going from a solid to a gas. Anytime that happens from a solid to a gas, we call that sublimation. And the opposite is deposition. So sometimes we call this thing the sublimation curve. And just a little bit more about that terminology. And when we call something, a fusion curve or a sublimation curve, something like that, what we're doing is we're saying that these, along this curve, so I'm on the sublimation curve down here, but along this curve, these are sets of conditions, pressures and volumes, so a pressure and a volume, a pressure and a volume, a pressure and a volume. Those are sets of pressures and volumes in which a solid will sublimate. There's also a couple kind of special points on every phase diagram, and I want to point them out. It's this point right here. Okay, so that's where all three curves come together. That is called the triple point. Okay, so it's called the triple point because it's in three different phases at the same time. They're all in equilibrium with each other. So at this one pressure and temperature data point, you will have a mixture of solid, liquid, and gas. All right, there's one more point that I want to talk about, a specific temperature and pressure. It's right up here. It's right where the vapor pressure curve stops. So at that one temperature and pressure, we call it the critical point. And at any higher pressure or higher temperature than the critical point, you get what we call a supercritical fluid. It's kind of like a weird fourth state of matter that's kind of like a liquid, kind of like a gas. It's not something that we ever see in nature because the pressures and temperatures are never really high enough, kind of where humans live, to see a supercritical fluid. But we can make it happen under some laboratory conditions. And even though it's not kind of a part of our everyday lives, you can really do some interesting chemistry with supercritical fluids because they have properties that are kind of like a gas, kind of like a liquid. Some things are only soluble in supercritical fluids. So at the end of this lecture, I'll kind of show you some pictures about what a supercritical fluid looks like. We'll kind of touch on it, but it's not something that we're really going to concentrate on. Now we've marked all the curves and the points on this example phase diagram. I do want to go to another phase diagram that it's the same, kind of just a slightly different picture cleaned up, so that I can talk to you about kind of moving through the phases. So when I say moving through the phases, I mean starting at a specific point and changing either the pressure or the temperature and seeing what happens to the molecule. So that's what I'm going to do. I'm going to start by just starting at this point right here. And if I start at this point and I start increasing the temperature, I'm starting at a solid And if I increase the temperature, I'm going to eventually melt it so I get to the liquid phase. And if I keep on heating up that liquid, so I'm at the same pressure, I'm just increasing the temperature, eventually I'm going to get to the gas phase. So now that doesn't really seem very exciting there. But I want to do it again because I know that almost all the time when we talk about changing phase, we talk about doing that by adding temperature. We talk about doing this exact process I just did here. But that's not the only way that we can change something's phase. It's much easier. I mean, it's pretty easy to heat things up and cool them down, but it's not the only way we can do it. Another way that we can do it is, I'm just going to start at this point right here. So I'm starting at the liquid phase. If I start reducing the pressure around that liquid, and if you're trying to imagine what that means, reducing the pressure around a liquid would mean putting it in a vacuum chamber and pulling it apart. I'm reducing the pressure to the point where I'm putting it under very, very little pressure. So I'm reducing the pressure. I'm pulling the molecules apart, and eventually I'll pull them apart far enough so they become a gas. So changing something's pressure is another way to change the phase. And that's not the way we normally do things because I don't have a gas chamber, or I don't have a vacuum chamber in my house. I do have a stove. So it's a lot easier for me to change something's phase by heating it up, and I have a freezer so I can cool things down. But it's harder for us to do this using pressure because we just don't, that's not very common equipment that we have. It's also not very energy efficient. Even when you think about your stove or your fridge not being energy efficient, pulling a vacuum on a liquid to make it into a gas to boil your water is not very energy efficient. So it's a way that we can do it. It's just not the way we commonly do it because of the type of equipment that we have. But those are all ways that you can change something's phase. You can change it by changing the temperature. You can change it by adjusting the pressure. So now we're back at the phase diagram that we had been labeling, and I want to talk about how we can use phase diagrams to mark boiling points and melting points. Okay, so the first thing I'm going to do is I'm just going to clean up this so that we have plenty of room to write. Now technically, I'm going to kind of concentrate on this curve for a second. Any pressure and temperature point along this curve is a point in which the solid will melt into a liquid or the liquid will freeze into a solid. So each one of these is a melting point. But which one of them is the normal melting point? Now remember, we defined normal melting point and normal boiling point at the temperatures in which the vapor pressure of the molecule is equal to atmospheric pressure. So atmospheric pressure, for it to be normal melting point or normal boiling point, it's the atmospheric pressure is 1 atmosphere or 760 millimeters of mercury. So when the vapor pressure of the molecule is equal to 1 atmosphere, that's what we call the normal melting point and the normal boiling point. So I'm going to draw a straight line across on this phase diagram that represents 1 atmosphere. I'm going to try and make it as straight as possible. Okay, so this is 1 atmosphere, or 760 millimeters of mercury, or torr, however you want to say that. And where that line hits the fusion curve, so right there, and where that line hits the vapor pressure curve, which is right there, that's what we consider the normal melting point and the normal boiling point. So melting points and boiling points are temperatures. So what we would do is we would go down, and whatever temperature this is, that is the normal melting point. Whatever temperature this is the boiling point. So that's melting point here and boiling point there. So let's see what that actually looks like for a specific molecule. Let's just look at water first. All right, this is the phase diagram for water. And you can see that it has a solid state, a liquid state, a gaseous state. And they've drawn a line at 760 millimeters of mercury. So that's sea level atmospheric pressure. And where that line hits the fusion curve, so right there, if you go down, that is the melting point for water. So remember, we talked about how melting point and freezing point are the same thing. For water, that's 0 degrees Celsius. Where that line hits the vapor pressure curve, or the vaporization curve, so right there where it hits it, we go down, that should be the boiling point of water, which the normal boiling point of water is 100 degrees Celsius. Okay, before we go on to some other molecules, I just kind of want to talk about phase diagrams in terms of kind of the big picture, kind of our environment. So I'm going to clean this screen up a little bit. All right, when we think about the environment and kind of the situations in which humans can survive, we can definitely kind of survive in the mid-temperature range. So I'm going to say that we are good from a little bit lower than 0 degrees to maybe about 50 degrees Celsius. Much higher than that, and we just can't take that kind of heat, and much lower than that, we freeze to death. So we can kind of survive in this mid-range of temperatures here. And then we can survive at a little bit higher than 760 torr and a little bit lower than 760, so that's about 1 atmosphere, or that is 1 atmosphere. We can survive a little bit higher and a little bit lower, but not much. Humans are really sensitive to pressure changes. If the pressure is too low, we can't get enough oxygen in our blood to survive. And if the pressure is too high, our blood vessels rupture. So what that means is that we can kind of survive in a very narrow pressure band right here. Okay, so what that means is I'm going to fill in the intersection there, this little blue box. Okay, that's going to represent the range of pressure and temperature conditions that humans are okay living at. Now that's a really small region compared to all the temperatures and pressures that are on this phase diagram. And I just want to point out that in this box here, there's a little bit of area where water is a solid. Most of the area, water is a liquid. And that kind of represents how we think about water. To me, when I think about water, I think about liquid water. Sometimes it's a solid, like if it's really cold. But in my life, water is not usually a gas unless I've dumped a bunch of energy into it. And that just is because humans can really survive over a small range of temperatures and pressures, and that's how we interact with water. It's a solid for some of those temperatures and pressures. It's a liquid for most of those temperatures and pressures. And because we don't have a very big view of water, we see it just in this little band here, it might be hard for us to think about how water has a sublimation curve. Now, every molecule has a sublimation curve. Some sublimation curves are long, some sublimation curves are short, but every molecule has a sublimation curve. There are pressures and temperature sets out there that you can get water to sublimate at, to go straight from a solid all the way to a gas, never reaching the liquid phase. But those are not regions that we really have on, that by regions I mean sets of pressures and temperatures that we have on planet Earth. They are really cold and at really high pressures, and that's kind of not a naturally occurring thing on the Earth. But there are situations in which you could get water to sublimate. Right. And now I want to kind of talk about intermolecular forces a little bit. I'm going to clean up this phase diagram. Now, some molecules have fusion curves that are more angled back like this, and some have fusion curves that are angled more in the other direction. And that's true. The sublimation curve is always going in this direction, and the vaporization curve, the vapor pressure curve, is always going in that direction. But the fusion curve can move in one direction or another, depending on what type of intermolecular forces a molecule has. So here's some phase diagrams. For some other substances, we have iodine, okay, so that would be like I2, and we have carbon dioxide. Now these have kind of large solid regions, and notice their fusion curves angle towards the right, just a little bit towards the right here. That's because they have weak intermolecular forces and they don't exhibit any hydrogen bonding. And so they have that kind of angled fusion curve here. If we kind of compare that, so I'm going to clean this up. If we compare that to what water looks like, the water fusion curve, I'm just going to draw it. I'm going to draw what water looks like on the carbon dioxide one. But water's fusion curve looks a little bit more like that. Okay, so that's what happens when something has hydrogen bonding. The fusion curve goes towards the left. When it doesn't have hydrogen bonding, it is more to the right direction. So I want to look at this carbon dioxide curve just a little more closely. So I'm going to kind of go to a bigger version of it. Okay, so it's the same curve. What I want to focus in on is this 1 atmosphere line here. Right, now remember that 1 atmosphere, that's sea level pressure. 1 atmosphere is the pressure that we use to define normal melting point and normal boiling point. And so what I'm going to do is I'm just going to kind of extend this 1 atmosphere line all the way across. Try and make it as straight as possible there. Okay, so when we were talking about this 1 atmosphere line before, we talked about how where that line hits the fusion curve, that would be the normal melting point. Where it hits the vaporization curve, that would be the normal boiling point. But here, when we write that 1 atmosphere line across, the only thing that it hits is the sublimation curve. And because it only hits the sublimation curve, that means that at 1 atmosphere pressure, kind of where humans live, the only thing that it's going to do is sublimate or deposit. It's not going to boil and it's not going to melt or freeze under the conditions that we usually witness it at. So at this point here, we call that the normal sublimation point, and that for carbon dioxide is negative 78.5 degrees Celsius. So if you pull it out of your ice chest, and if you're in an environment anything higher than negative 78.5 degrees Celsius, it's going to sublimate right away. And okay, so I said earlier that later in the video I would talk about this idea of critical point at which a compound becomes a supercritical fluid. So I wanted to just kind of show you some pictures about that. So the critical point is made up of a critical temperature and a critical pressure. The critical temperature is the highest temperature at which a substance can exist as a liquid. Anything higher than that, and it's going to be a gas. And then the critical pressure is the pressure required to liquefy a substance at its critical temperature. So when you've reached the critical pressure and the critical temperature, anything higher in either direction, you're going to get a supercritical fluid. It ends up that the stronger the intermolecular forces, the higher the critical temperature. So something with really strong intermolecular forces would have a very high critical temperature. You'd have to heat it up really hot to get it to turn into a supercritical fluid. Now when we say supercritical fluid, what we're really talking about is, like I said, maybe kind of like a 4th state of matter. We don't actually call it the 4th state of matter because it has the properties of both a liquid and a gas. It's not really anything new. It's kind of both of them together. We say that the liquid and the gas phases are indistinguishable, and I'll show you a picture to kind of show that. So it has motion like a gas. The molecules are moving a lot, but they have enough room in between them so that they don't feel intermolecular forces. So they have a motion like a gas, but they're relatively high density and it can actually flow. So here's a picture of carbon dioxide becoming a supercritical fluid. In the first picture, what we have is the liquid phase at the bottom and the gas phase at the top. And that's kind of usually how we see gases and liquids. Gases are less dense, so they come to the top. Liquids are more dense, so they go to the bottom. What you see this in is just a little chamber, and it's a chamber in which they can change both the pressure and the temperature. So as we move from the first picture to the second picture, I'm going to look at this phase diagram down here. So what we're doing is we're starting here, so that is picture 1, so that's kind of like situation 1. And as we're moving to the middle picture, what they're doing is they're increasing the temperature and they're increasing the pressure until you start to see a supercritical fluid start to form. So here, the meniscus, so the line between the two, that meniscus becomes less and less distinct, and what we see is kind of a gas phase, a liquid phase, and in between, a supercritical fluid is starting to form. So as we get to this phase, that is where we have reached the critical point. Once we've reached the critical point, there isn't a gas, there isn't a liquid. It's kind of like a mixture of both of them. So you can kind of think about it as a super dense gas or a less dense liquid. You can think about it as a gas with not a lot of space between the molecules, or a liquid in which the molecules are moving very quickly, but it's kind of like a gas and kind of like a liquid. That's what we call a supercritical fluid. And we call it a supercritical fluid because it flows like liquid, even though it has a lot of gas-like properties. So in this video, we talked about the phases moving between them, what we call those transitions, like sublimation, deposition, things like that. We also spent a lot of time talking about phase diagrams, what their curves and regions were called, what happens when you start at a point and you increase pressure or temperature, how you move through the phases. And then we talked about using 1 atmosphere of pressure to define normal boiling point and melting point. And we also touched on supercritical fluids.